Princess, good evening.
Very good evening, everyone, and welcome to the sixth episode of the Iris 2.0 webinar series. Today, we are delighted to provide you with a bird's eye view of the Center of Excellence for Studying Critical Transitions and Complex Systems, abbreviated as CTCS. Critical transitions are marked by abrupt shifts between different states that impact various complex systems, ranging from climate and thermo-fluid systems to power grids, infectious diseases, and financial markets. The consequences of these transitions can be severe, leading to extreme weather events, space mission failures, blackouts, ecosystem collapse, and financial market crashes. The focus of our discussion today centers on the CTCS Center of Excellence, which delves into the study of critical transitions and extreme events in flow and energy systems within both natural and engineering contexts. Specifically, the center's exploration will encompass transitions in thermofluid machinery and extreme events occurring in climate systems. Allow me to introduce Professor R.A. Sujit, the principal investigator of the CTCS Center of Excellence. Professor Sujit, a distinguished academic, received his B.Tech in Aerospace Engineering from IIT Madras in 1988, and went on to complete his MS and PhD at the Georgia Institute of Technology, USA. Joining IIT Madras as a faculty member in 1995, he currently leads the Center of Excellence for Studying Critical Transitions in Complex Systems. Professor Sujit's impressive accolades include the Alexander von Humboldt Fellowship, the Hans Fischer Senior Fellowship of the Institute of Advanced Study at TU Munich, and the Swarna Jayanti and J.C. Bose Fellowships by the Department of Science and Technology of the Government of India. He is a distinguished fellow of the International Institute of Acoustics and Vibration and a fellow of various prestigious institutions, including the Combustion Institute, the Indian National Academy of Engineering, and the Indian Academy of Sciences. Recently, he was elected as an international member of the US National Academy of Engineering and received the Lifetime Achievement Award from IIT Madras. Professor Sujit's primary interests lie in complex system theory with a specific focus on thermoacoustic instability. A warm welcome to Professor Sujit and his team, as well as our distinguished moderator for today, Professor Maria Hector. Now I'd love to introduce Professor Hector. A physics graduate from the Technical University in Berlin, Professor Hector completed her PhD in 1985 on heat sources in acoustic resonators at the engineering department of the University of Cambridge. With an impressive academic journey, she served as a lecturer in applied mathematics at Kiel from 1992 to 2000, later becoming a senior lecturer from 2001 to 2013. Currently, she holds the position of Professor of Engineering Mathematics at the School of Chemical and Physical Sciences of Kiel University. Professor Heckel's contributions to research are substantial, with a research grant income exceeding £10 million, over 80 published articles, and a patent on reheat bus control. As a fellow of the International Institute of Acoustics and Vibration, she plays an active role in shaping the field. Professor Heckel's commitment to environmental research and gender balance in scientific research is evident in her passion for projects that benefit the environment and promote inclusivity. Her research interests focus on physical acoustics with industrial applications, particularly in the areas of noise control, instability control, and non-destructive testing. Join me in extending a warm welcome to Professor Heckel, and without further ado, let's get started with today's session. Over to you.
Thank you very much for this kind introduction. It's a great pleasure for me to act as moderator for today's webinar. I know Professor Sujit very well. We have collaborated for quite a few years, and in particular, we have collaborated on two European-funded grants, large-scale grants, research networks sort of involving several PhD students. One was called Tango, and the most recent one was Polka, which just finished a few months ago. And Sujit was instrumental in helping with ideas to set up the grant and also supervising PhD students. And it's a great experience to work with Sujit, and I hope I can carry on doing that with him for many more years. Both Professor Sujit and I share a passion for studying thermoacoustics, in particular the nonlinear aspects of thermoacoustics. And these include abrupt transitions from one state of another, for example, from a steady flame would be one state, to a violently oscillating flame another state. And the transition between these states can happen very, very quickly. This kind of thing doesn't just happen in thermoacoustics, it happens in other real-world scenarios. And Professor Suchit will take us on a journey today to explore about abrupt transitions in a wide range of systems.
Thank you, Maria. I will share my screen now. Can you all see my screen?
Fine.
Okay, great. So, good day to all of you. And I want to thank Maria for her kind words. And I want to thank all the attendees and all the panelists and all the collaborators for taking time to attend this talk. And before I start, I want to thank IIT Madras for granting me this Center of Excellence, and also all the funding agencies so far for sustained funding. I will acknowledge the names in the end. And I also want to thank, most importantly, my collaborators and my incredibly bright students and postdocs and staff with whom I worked over the years. What's a complex system? Let me get this thing out of the way. It's blocking my view. What's a complex system? A complex system is a system that has a large number of constituents which are interacting with each other and whose properties cannot be inferred simply by looking at the properties of the individual constituents. And in other words, for a complex system, the whole is more than sum of these parts. And complex systems show what is called emergence. So emergence occurs when the complex system has properties or behavior that its individual constituents do not have on their own, and emerge only when they interact as a wider whole. So the classical example that they give is the wetness of water. So water has H2O molecules, but no amount of zooming in on the H2O molecules will give you any idea of this property called wetness. It is meaningless at the level of the molecules, but when a large number of molecules, say Avogadro number of molecules, interact with each other of that order, then we see this property called wetness. So emergence is a characteristic of complex systems, and complex systems undergo critical transitions. During a critical transition, the system abruptly shifts from one state to another state for a slight change of control parameter. And for example, a slight change in climate can lead to the collapse of an ecosystem. And examples of critical transitions include epileptic seizure, spontaneous asthma attacks, and financial market crashes. And critical transitions are occur in thermo-fluid machinery also, like jet engines and rockets and so on. So in this movie, which is playing now, it's movie of a F1 engine of the Apollo program, the moon rocket, exploding during the static test due to thermoacoustic instability. And thermoacoustic instability occurs as a result of positive feedback between sound waves and flame in a combustor, leading to ruinously large amplitudes. And thermoacoustic instability leads to catastrophic failure in rockets and aero engines and power plants. And in general, critical transitions have undesirable or even catastrophic consequences. Nature unleashes its fury through critical transitions, and extreme weather and climate-related events adversely affect the society, causing death, injury, illness, trauma, and adverse socio-economic impacts. We just had a flood in Chennai a week back, and it was disastrous, and many parts of the city are still reeling from it. And these images are from the 2018 August floods in Kerala, in which my own ancestral home was completely drowned, and like there's a picture of a helicopter doing rescue. Many people had to be rescued from the top of the house in this manner. And this really took an emotional toll on me. That's when I decided that I should work on such transitions also. While this Kerala floods was happening, some other parts of India had drought actually, where one place is flooded with water, other place has drought. And also we can see that the forest fires are becoming more frequent in many different parts of the world. And the climate changes cause changes in extreme event and frequency and geographic distribution. And this whole world is connected, because I do something bad, but you may be affected. And if you do something bad, somebody else could be affected, because the whole world seems to be connected. So the effects are not just local anymore. So we study critical transitions and extreme events in flow systems in engineering and nature using the framework of complex system theory. And there are three classes of systems that we are looking at. One is transitions in thermo-fluid machinery we want to look at. Then we want to look at extreme events in climate. And I want to also look at onset of precipitation in clouds. We endeavor to elucidate the commonalities and structure of these transitions in diverse systems, because although many of the systems are different, totally different physically, but there seems to be underlying unity, underlying commonality across the systems, and that's something we really endeavor to elucidate. Now, the behavior of the complex system is often independent of the details of the system and are driven by interaction that span an enormous range of scales. Now, on the left, I have a picture of a thermoacoustic system, which is an engineering system. On the right, we have our climate system flow around the globe, and both are turbulent thermofluid systems. And these are characterized by a large range of scales and degrees of freedom with feedback loops across subsystems. Now, when you have turbulent flow, and in thermo system, we have acoustic and vortical waves interacting with the heat released by the flame. In the climate system, we have winds and ocean currents, and of course there is heat release rate, but in this case it's not by burning fuel, but it is by a condensation of droplets releases heat. And so these are large complex systems, and to model such thermofluid systems, we need to encode these interactions, and that is where the complex system theory comes. So we are studying engineering systems, and we study a class of many different systems, such as thermoacoustic system, aeroelastic system, aeroacoustic system, with the aim of not just studying them, but we want to unravel their commonalities. And climate is also a complex system, as climate is associated with interactions within and across multiple subsystems, such as land, atmosphere, ocean, and biosphere. So the interactions lead to climate phenomena, and dynamics occur over a wide range of spatio-temporal scales. So in the systems in nature, we are just like so far we talked about engineering systems, but now in nature, we investigate dynamics of multiple subsystems across multiple spatio-temporal scales in the climate system. So we are looking at microscales. In microscale, role of turbulence in cloud formation. In the synoptic scale, we look at genesis, intensification, path, and prediction of tropical cyclones. And in the seasonal and planetary scales, we look at teleconnections due to large-scale phenomena in general atmospheric circulation. We will study both intrascale and interscale interactions. So interscale and intrascale interactions between multiple subsystems are responsible for critical transitions in a complex system. And it is critical transitions in climate system that leads to extreme weather, such as cyclone or floods and so on. Now, the question is, how do we encode these interactions? Complex system has a large number of highly interconnected interacting components. So we encode these interactions into complex networks. A complex network comprises of nodes, which represents the components of the constituents, and links which represent the interactions. So these connections can be physical, as in the case of an airline network. For example, when you get into an airline, you open the magazine in the seat pocket, you can see each of them will draw their network. So airports are the nodes here, and the flights carrying the passengers are the connections. So that's the interaction. In thermofluid system, this is not we don't see any physical connection, but the connections are hidden, they're abstract. So how do you do, what machinery do we have to construct complex network under those cases? So what we do is we have so many grid points where each of the points we have variables, we have time series, and we look at correlation to compute the kind of similarity that we have. And if the correlation is above a certain threshold, we'll connect the nodes, and the correlation is below a threshold, we do not connect the nodes. So such networks are called functional networks, and complex networks help us unravel hidden connections and track their evolution. And in addition to this kind of network based on statistics, we have also constructed physics-inspired networks. So here is an example of that we have introduced this physics-based network in the climate science for the first time. So two cyclones can come within a close proximity, which may lead to strengthening of cyclones or even completely merging into one cyclone. So the interaction between two neighboring cyclones before the complete merger is not well explored. And it's a major challenge for the weather forecasters and policymakers. So we construct a time-varying vorticity network using the Biot-Savart law to study cyclone merging, so that the induced velocity is the strength of the interaction. And using complex networks built from Biot-Savart law, we capture the dynamics of physical flow field during binary interaction cyclones. This work was done together with PIC, with Kurtz and Marwan and Shraddha, and also funded by ONRG, and recently appeared in Chaos Journal. In climate networks, we have multiple layers comprising ocean, land, and atmospheric subsystems with interactions across layers. So we have wind velocity, temperature, precipitation, and cloud cover. And in a similar manner, in a thermoacoustic network also, we have interacting subsystems, and we have multi-variable coupling due to the interaction of the subsystems. So recently, we have published this work in Journal of Fluid Mechanics, where we use multi-layered complex networks. In one layer, we have data from the hydrodynamic field, which is the vorticity layer, and the other layer, we have data from the acoustic field and the combustion dynamics, that is the thermoacoustic power. And we discovered intense inter-system interaction occurring in localized pockets, as you can see, in the recirculation zone. So these regions, which you can see as the red color region, these occur prior to the onset of thermoacoustic instability. So even before thermoacoustic instability happens, you see very intense interaction in certain regions. And we have developed early warning signals, which are called EWS in popular literature, or precursors. And these can help us to avoid this, or we can also develop strategies to mitigate these transitions. So imagine a system, let's say a gas turbine system. Of course, I am showing the data from a laboratory combustor, and I increase the flow rate or the Reynolds number, and the signal looks like this. I mean, this, what I've plotted is a RMS value of the pressure and the FFT, and you see a gentle slope upwards perhaps, but then you don't know whether it's just more flow, more turbulence, or is that the case, or is there a impending transition that is coming up and you're going to jump into a large amplitude oscillations. So can we look at the first 5-6 points where nothing has happened and say that the one on the left is okay, there's no crisis, and one on the right is actually we are headed towards an impending transition. And so idea is to prognose the onset of an impending instability. And so the pressure amplitude goes up, you can see a bit later, but even as the pressure amplitude doesn't change, you can examine the first 10 or 12 points, we can see a Hurst exponent, which is actually a precursor measure, which is 2 minus fractal dimension. It is changing well in advance. So there are many such measures which give early warning, and we can use them, and they will help. This prior knowledge of the proximity to thermoacoustic instability will really help us, and these measures tell us the proximity to the onset of this transition. Also, estimation of amplitude will be useful, and we have shown that the amplitude has an inverse square law scaling with the Hurst exponent. So amplitude is proportional to 1 over Hurst exponent squared, but we also have many other scaling relationships. And these, interestingly, these relationships hold across many systems: aeroacoustic, swirl system, different type of combustor system, aeroelastic system. So this is what I mean by the universality, there is, or commonality across subsystems. In fact, some of the scaling relations hold across electronics, CHUA circuit, and laser systems, and so on. And we have a number of patents on this topic, about 15 patents, and we have developed this precursor technology, which is implemented in the industry. It works very well. And I also want to once again harp on this idea that disparate system can exhibit similar behavior. I want to go on step extreme, talk about COVID. So extreme COVID-19 waves exhibit hyper exponential growth and log periodicity close to a critical point. And this was there for whenever you have sharper than exponential curve, there's a singularity and rises very sharply. And that's what happened during the Delta wave in India in 2021, where there was, it wreaked havoc here. And what is interesting is that flame blowout, which is a completely different system. There's nothing common between flame blowout and COVID, but except that they're complex systems. But flame blowout is also preceded by hyper exponentially growing low amplitude oscillations decorated by log periodicity. So the log periodic power law can be used to predict the critical points. So we use a data-driven complex system approach supported by machine learning to map the evolution of hidden patterns and connections. So we'll use tools from complex networks, fractals and multifractals, recurrence quantification, and synchronization theory. So we have been quite successful in these tools. In thermoacoustics, we identified and modeled hidden patterns in multi-layered data. We could do extreme event characterization in flames. We could do regime transitions and early warnings, which I just spoke about. And we also have developed smart control strategies where you can find critical region hubs in the flow, which you can gently disturb, and we can, by gently tweaking the flow field by cooling air and so on, we can actually shut down the instability. Now we want to expand this to complex system theory in general, such as climate system or epidemiology. So we want to develop tools for early warning of critical transitions and extreme events. We want to mitigate transitions and their effect through smart control actions. Of course, this is for engineering systems. We cannot control nature, but maybe we can manage natural calamities by floods, etc., by more judicious usage of, dams. And we want to translate the understanding to inventions, patents, products, and startup incubation. And we also want to disseminate the technology and the knowledge that we develop to a diverse audience across the globe through webinars, short-term courses, and workshops. At the center stage is data. And we use satellite-based data for studying climate networks. There are many different data sets available. And we have a number of well-instrumented rigs to study transitions in fully turbulent thermo-fluid systems. These include, but not limited to, swirl and bluff body stabilized turbulent combustors. And we have also a combustor with a preheated air, because the air coming from the compressor will be hotter. And we have annular combustors in which we can have axial, annular, or combined modes. So here we have axial mode. On the left, you can see the stable operation. So the flames are fluctuating in a periodic manner, which are not synchronized. On the right, you have thermoacoustic instability. So we have periodic flames which are actually synchronized. We have a facility to have cloud in a lab. So we have made a turbulence chamber to study cloud formation. Also want to acknowledge ISRO for this. And we are studying the role of turbulence in rain cloud formation in this setup. So we acquired spatiotemporal data with high temporal and spatial resolution from experiments, and working with real data gives us a significant advantage to connect the dots it pays to generate real dots. So the center endeavors to unravel the science behind critical transitions in diverse systems, to develop translational technologies, and to develop trained human resources. Now, in the short term, we'll develop tools to predict, avoid, or mitigate instabilities in thermofluid systems. We'll contribute towards ensuring energy security, national security, and access to space. We'll develop predictive models for cyclones, atypical Indian monsoon, and the ensuing extreme events, and obtain local and global precursors. And our vision for the long term as in a decade, we should be able to develop many technologies that enable critical interventions and provide guidelines for sustainable development, accounting for increased variability in weather patterns, and generate transdisciplinary insights and provide society and government with reliable information for sound decision making. We have a monthly webinar series of eminent speakers. These are like the stalwarts or giants in the fields, and I'm so proud that we are able to run it every month. And this series is co-organized with Potsdam Institute for Climate Impact Research, together with Professor Jürgen Kurz, who is here in the audience. We are also organizing a biannual workshop on the application of complex networks to fluid dynamics, and we are able to bring together researchers across discipline who use complex networks to study thermofluid systems. We have, in summary, established a synergetic coalition of leading experts across disciplines in the last decade or so, and we collaborate to solve complex problems. Some of the problems are really hard. They're grand challenges, either be it thermoacoustics or oscillatory instabilities in thermo-fluid machinery in general or in climate systems. And global collaboration transcending disciplines enable us to tackle grand challenges. I could not fit in everybody's picture into it, so I'm sure I missed out many of my collaborators. Sorry about that. And I want to thank you all for attending this talk at different times of the day. And I also want to take this opportunity to thank the sponsors who have been very generous and in funding us for a sustained fashion. Thank you.
Yeah, there we go.
I'm done.
Thank you. Thank you very much, Suchi. Are you happy to answer questions?
Yes, I'll be very happy.
Right. So I've seen there are a number of questions have appeared in the question and answer box.
Yeah.
So I'll just read them out in the order in which I see them. So one question from Supam Diora. The question is it possible to create thermoacoustic waves instantly in a controlled manner to increase efficiency of fuels?
Yeah, it's possible, and that's the whole idea about pulse combustion. So if we can manage that the hardware doesn't go wrong, then we can have it. And industrial burners, people have done that.
Okay. Then the next question is from some anonymous attendee, and they are asking the following. Could you please indicate any studies or literature which have used similar interaction mechanics for biological systems, in brackets in vivo? Hang on, I've lost it.
Yeah, I think there are a lot of
cross interactions.
Yeah, there are lots of studies. In fact, the subject is very advanced, so we should be able to easily Google search and get it. There are plenty of literature.
Then we have a question from Prabin Bandari. How does critical transition of complex systems impact on energy economics? The text is jumping around. I find it very hard to read it.
Yeah, I read it. Yeah, I got it.
Of energy systems.
Yeah, so I think in a local level, critical transitions would actually restrict the stability limits of the operating system. But on a major scale, a critical transition can lead to blackouts and so on, and whole parts of country. I think there was a big blackout in Germany some time back. I have seen Jürgen's presentation, and also in the Northeast India, there was a blackout some years back. So those are when a large number of interacting systems all fail together. And so it is definitely possible, both on a local scale and at a global scale.
Okay. Then we have another question from an anonymous attendee. Most of the examples mentioned in the presentation demonstrate to exponential growth due to critical transitions. Are there any examples where exponential decay occurs due to critical transitions?
I think there are many examples. I'll mention one example, that is we have a forest getting desertified. So that is a place where the vegetation decays, actually.
Okay, I just see a hand. Wolfgang has his hand up. Do you have a question, Wolfgang? You are muted.
Sorry, I didn't want to jump the line. I didn't realize I was looking for the applause button, but I didn't find it. But now that I lower my hand. But now that you prompt me, I was wondering. You said there are networks, say in fluid dynamics systems, where you construct a network and its structure from correlation, but correlation ignores causality very often. That's an issue I sometimes take with studies in medicine. And I was wondering, in critical systems, is that, in network theory, is that not a significant loss, that correlation by itself does not tell you anything about causality?
Yeah, I think that is all right if you look at self-evolving system where causality is not very important. But if you are specifically looking for causality, I think you have to be careful. But if you are looking at self-evolving system, like chicken came first or egg came first, so then this is in the case of an evolving system, I think it's not important. But if there's a cause, you do something and something happens, then I think this is an important thing. And there are actually directional methods where we can actually find how one system affects the other. So there are metrics which tells the directionality of even if in a self-evolving system, there are two systems co-evolving, you can tell with directional measures like cross transitivity or certain I don't remember the names, all the names, but there are measures which can discern the directionality. So
Okay, and self-evolving means that you have interaction over a number of generations or a number of cycles somehow. Is that the
right.
idea behind this term, or?
Yeah.
Okay. Good. Thank you.
Okay, thank you. Then another question from the question and answer box by Arnav Agarwal.
Yeah.
How does the cloud creating machine work?
Okay, so the cloud creating machine, what we do is to inject droplets with fine ultrasonic atomizer, and we simulate the turbulence by using fans. This machine was designed by a friend of mine, Shweta Pro Chowdhury, who is in Toronto. I guess he is around. So we can, by adjusting the RPM of the fans, we can get the required level of turbulence, and we can require we can tailor the number density distribution by playing with the atomization. Also, we can tailor the total number of droplets also. So that's in short.
Okay, thank you. Then we have a question by Arya Kulkarni. The question is this: what are your opinions on use of geoengineering for control of climate change? Will cloud seeding, iron fertilization, etc., have any long-term effects on the Earth, and will we be able to foresee them?
First of all, I'm not qualified to give a proper expert opinion, but since IJ is asking for my opinion, I would say that my opinion is that don't tamper with nature too much. Just so it would have unintended consequences, I would think. But again, I am not qualified to really give an answer for this.
Yeah, thank you. Then we have a question by an anonymous attendee. What measures can be analyzed to understand the nonlinear behavior of the flame dynamics?
I think it's a very too general a question, but
yes.
I think in a global sense, we can look at the flame transfer function in its various forms. I think that would be a simple answer.
Okay. The next question is also very generic, so I'll move on to the question by Purva Srivastava. The question is, how long does it take for use to detect and give warning for critical transition about to occur?
A very interesting question, and one can't give a very general answer, but the two things. One is the time you have, and then the frequency at which the phenomena happens. For example, I can give an example for an engine. You need to accumulate certain cycles of data to be able to make a meaningful calculation. And how does this compare to the time we take to make the changes? So in a land-based gas turbine engine, the change happens of the order of 10 minutes or 20 minutes. You change fuel and so on. And the typical calculation time would be of the order of a second or lower. And exact time depends on the exact situation. But in an aero engine, for example, if you have a fighter plane taking off 0 to full thrust in 5 seconds acceleration, then you would, I think still you can manage to get it because you have a quarter second to get the calculation done. So it is enough time, I think.
Okay, thank you. And then a question by Surendran Iyer. Can you please let me know about critical transition studies with respect to protein modeling and folding?
I'm sorry, I don't know anything about this subject. Actually. I think it's too wide. Yeah.
Okay, then I'll move on to by Amun Chowdhury. What is the application of critical transitions in fluid mechanics?
Yeah, I think there are a lot of applications. So we call it instabilities, but they are actually critical transitions. And in turbulent systems, we go from aperiodic oscillations to periodic oscillations. And we can actually be forewarned, not just in thermoacoustic, but in other instability system like aeroacoustic, aeroelastic, etc. And another interesting transition is flame blowout, where the flame just comes out of the engine. So we can get early warning to these critical transitions. We can also devise strategies to like smart control strategies to we can look in the complex networks. They often have a hub structure, and if you can detect where the hub is, and you can take it out with gentle action, and then the whole network will break up, and you will have then we'll be able to get back the stable operation.
Okay, thank you. Then there's a question by Prashant Singh. You talked about your studies on interaction between two cyclones. What kind of interaction were they observed to have? Could it be solitary type, or will it be dissipative, or something more complex?
In general, they can dance around, or they can merge, and they can pass without doing anything. And the ones we studied were two cyclones merging to form a super cyclone. So that's what we studied. And it dissipates once it makes the landfall.
Okay, thank you. And then there's a question by LS Nivedita. Is there a way to identify which metric will point us towards identifying a critical transition for a specific problem, or is identifying a metric a trial and error method?
I think in general, having a domain knowledge is very good, so that you would be able to do. But I think there are matrices which can detect certain bifurcations in general. And I think some things work, but I think for a class of systems, so I think it's not totally terra and error, but if you have already worked on the subject, you would have a feel for it, and I think you would be able to pick the right ones. But of course, I would, if I were a manager, I wouldn't go in anything without playing with all the existing data. I would run by this methodologies to get experience before installing anything in a real system.
Thank you. Then we have another very generic question by, by Chandra Kala Meena. Some transitions are very fast, like blackouts, and some are very slow, like landslides. How are we able to capture slow and fast transition using complex dynamical theory?
Yeah, I think this is still there's no clear answer, still a work in progress, and a lot of papers still come out. So I am not able to give a final word on it, but I think we can capture slow and fast transition. But the important question is, even if you capture this, is there time for taking any action? So that is the important question here, I think. So which is ongoing work, actually.
Okay, thank you. And here's a very specific question. It was mentioned that there are monthly webinars discussing research on complex systems. Can normal, i.e. non-researchers, participate or attend these webinars?
Absolutely, anybody is welcome, and you can search our website, see critical transitions in complex systems, and register for the webinar. And if you're unable to do so, send me a mail and I'll get you. And we are most happy to welcome anybody.
That's good news, thank you. A question by Supam Diora. Are cosmic rays have similar effect as thermoacoustic waves on satellites, and how are they controlled?
I have no clue about this. I'm really sorry.
Okay, right, we'll move on. Question by Tusha Yaiswal. How do human activities and interventions impact the likelihood or occurrence of critical transitions in various systems? That's a very generic question.
Yeah, I think this definitely influences, and also also the rate at which the parameters changes. That's also important. So there's something called R tipping. So where maybe if our temperature changes by 2 degrees over 100 years versus temperature changes by 2 degrees over 10 or 15 years, there will be a big change. And so I think humans can accelerate the rate at which this change happens. And then we can actually, there have been conjectures that there can be R tipping, rate-induced tipping. And so that is one way humans can mess up things.
Okay, thank you. Here's another question. Are there alternative methods for flood control without relying solely on dams?
Yeah, I think this is also, I'm not a hydrologist, but
yeah.
from seeing the local thing. So Kerala and Tamil Nadu are on east and western sides of India. The Kerala is a place with excess rain. So all the strategies are towards somehow getting the water flow into the sea. In Tamil Nadu, rain is less. So everywhere water is collected in ponds so that we prevent under any cost water going to the sea. But the problem that happened over the last 200, 300 years is that these ponds were not maintained well. So there was this underground set of, I don't know, something like underground river, underground water that is messed up, and this paths to refurbishing that's messed up. But yeah, I think these are two methods of flood control that I have seen here in east and west side of India. But really, you should ask this to a hydrologist. I'm not really an expert on this.
Thank you. Then there's a question by Niraya Varma S. How are you making use of machine learning in your application?
Yeah, I have done some work on machine learning. For example, we use recurrence analysis, and then we can actually get recurrence networks and then identify the pattern with machine learning and like CNN or something. And then we can actually get a measure with which we can know the proximity to instability or the onset of the transition. Another idea we used is neural network, and also together with Potsdam. Potsdam is pioneers in using machine learning to do even things like phase space reconstruction and so on. So I think there's a lot of applications. I've just scratched the surface, but there's a lot of work to be done.
Mm-hmm. Thank you. Then we have a question by Naresh B. He asks, or she, can you give about climate change critical transition?
Oh, I think I'm not an expert on this, but the temperature rise is there, and when the temperature rise is there, and like I said, one thing that I want to talk about is this rate at which the temperature changes that can affect the transitions. And if we add CO2 at a very high rate and increase the temperature at a high rate, we can actually get this R tipping, where the Earth can tip to some other climate which may not be suitable for human habitat. Because Earth, we had ice stages and also full without ice. So there have been several stages, and these kind of things happen usually on very large time scale. And species perish when they cannot adapt to these changes. But we are now seeming to have very accelerated change.
Okay, thank you. And then here we have a question from an enthusiastic computer science student. They ask, how can I do practical contributions to this field as a computer science student?
Yeah, I think complex network is a lot of computer scientists work on this. They're, of course, machine learning. And you can actually construct complex network and unravel the patterns using machine learning. So I think computer science students can do a lot on this, because and then you can apply this to climate networks or any kind of network. So I think there's a lot of potential for doing this.
Mm-hmm. Thank you. Then the next question is by Vaishnavi MS. Are there specific regions or ecosystems that are particularly at risk to critical transitions?
I am not in a position to give a good answer to this. Yeah.
Okay. Yeah, I'll read it out. The question: will not our preemptive interventions after the system or a closely coupled system, if not immediately and drastically, leading to another potential critical transition, won't disregarding causality make this worse?
Yeah, I think if you do some intervention on a complex system, it would, of course, make the system come to a more desirable state, but you can also make it go to a much worse state. So that is definitely possible. So I didn't understand the last part, but I'm not saying you should disregard causality.
Thank you. Oh, here's a nice question by Sri Advaita Varakavi. How do you facilitate collaboration between researchers from different disciplines within the Center of Excellence? Are there specific challenges in integrating knowledge and methodologies from various fields to study critical transitions?
Yeah, I think the key thing is that it takes a lot of effort to understand the person in the other field. So when I started out, I wanted to use the tools from critical transition to study thermoacoustics, but nobody had done that. So I was reading other subjects like two subjects in particular, complexity medicine and climate science. That's when I made my trip to Potsdam to meet Kurz and Norbert Marvin, and I learned what they were doing. So you have to, the challenges are, first of all, you won't understand what another person is doing because it's a different area. And then you have to learn a lot on that subject. And then you have to make them understand what you're doing. And so that is those are the challenges. But this complexity theory has been lately getting a lot of attention in the Nobel Prize in 2021 came to that. And I think the people who work in complex system theory are very aware of this, and they make an effort to make other people understand and so on. And there are lots of review articles on this topic, which are written for the general audience. I mean, not general public, but general researcher. So, and the writing usually is very good because people from biology to neuroscience to climate to engineering to physics, everybody reads these papers. So I think there's a challenge, but I think help is available.
Okay, thank you. Here's a local question. Is there a short-term course, something like 3 to 5 days, to get comfortable with complexity science, somewhat generic to engineers and scientists, something planned at IIT Madras?
Okay, at the moment, IIT Madras has a 2-year master's program on complexity, but maybe we'll try to set up something for 3 to 5 days and announce it in the not so far future.
Crash course, yeah. Another question by Supam Diora. Do we have any relation of quantum physics to critical or complex systems?
I don't know anything about quantum physics, so I really shouldn't answer this.
Okay. And this is the last question in the box. There are several parameters responsible for critical transitions. Say 2 parameters have the same effect over time. How do we determine which one is dominant and would lead to chaos?
I think you'll have to get a full map of the what engineers call stability map, and we'll have to look at different parts of the stability map, and there's no easy way out around it. So you'll have to do a comprehensive calculation.
Mm-hmm. Thank you.
But maybe
now, please answer the questions in the box. I see Andrea De Vita has got his hand up. Do you have a question, Andrea?
Yeah, a question indeed. Do you hear me?
Yes,
I can hear you.
Fine. I wonder if your institution, Professor Sujit, works with non-equilibrium thermodynamics as well.
Yeah, I mean, yes, there are people who work on that. Yeah, I think definitely yes. Yeah, I am not fully into it, but just trying to. I come from engineering framework and also looking at other systems like climate, but the backbone of all this is non-equilibrium thermodynamics. So yeah, it makes sense to go after that. Yeah. Thank you.
Thank you. Are there any other questions from the audience?
Or maybe comments from the panelists also would be welcome.
Yeah, I would like to ask a question. You mentioned in your talk that you have actually implemented your precursor technology in industrial systems. Can you be a bit more specific, please?
We had, before COVID, this was used by General Electric for some time. And then in their energy producing engines by GE Power and Water. And with the space program, we were looking at liquid rockets where we were looking at EWS measures as a measure of proximity to instability rather than using the amplitude. So that was not as a early warning itself, but we were using it as like a measure. So this was in the liquid engines here.
And is this running on a permanent basis, sort of monitoring?
No, it's not running on a permanent basis.
Okay, thank you.
It was used in the laboratories to speed up the test.
Mm-hmm. I see we have a question by Ramesh Kolar.
Hi, Ramesh.
Please.
Hey, good morning, everyone, and particular, Sujit. This is Ramesh. Very wonderful overview of all the works you've been doing in your team. And I just had a comment as another suggestion. You worked with several systems. It will be nice to have a common. You were also mentioning about commonality and universality. So if there are two systems totally disparate or different, if you study one of them, the metrics that you are developing, will that be useful for other systems? That's one question. And second is we did talk about it a while back about application to the human body, in particular, the transition, the criticality for the human. I personally experienced something with a relative of mine, is the stroke in the brain. And even if one day advanced notice, somehow you can study various biometrics or human thing, whatever time series that would be, to predict as a precursor to impending stroke, hemorrhage or blockage or any of those would be very helpful. I know you did exercise trying to collaborate with people. That would be still a good thing to continue, so it will be useful for a whole bunch of people worldwide.
I will. Now I've forgotten the first question, but I'll answer the second question. We have started working on the biological systems, and we hopefully will make some products which can help prevent or get early warning to stroke or sepsis or heart attack or something like that. My mom herself died because of the stroke. So I'm very sensitive to this, and I'm quite interested in working on it. And we are now starting to work, but it will take some time. About the first question about metrics in one system being applicable to another system, I think there are a class of systems which behave in the same way. So the key is to identify the class of, so it's not as, the universality is not as strong as in the case of equilibrium thermodynamics, but these are non-equilibrium systems. So there will be certain class of things which will behave in a certain way. And I think we'll be able to identify. So a specific example I would say is, for example, the scaling that we got with Hurst exponent, that worked for our turbulent system, but they were not working for other systems. But whereas some other scalings with spectral measures and so on, it had a wider application, including things like lasers and so on. So I think we have to, the challenge is to identify the class of systems for which these commonalities and or soft universalities apply. Did that answer your question?
Thank you. Yes, you did. Yes. And maybe offline we can chat a little more on.
Andrea has another question. Andrea, do you have a question? Your hands.
Yeah, there's another question by Andrea De Vita.
No more.
Okay.
Oh, you haven't put your hand down. Okay.
Sorry. Sorry.
Don't worry. Any more questions from the audience? So is it time for me?
Norbert is saying something. Go ahead, Norbert.
Okay, I just have not a question, I have just a comment, because Sujit also mentioned our collaboration, and I also would like to say that it's really a very fruitful collaboration, and I have learned a lot. And this is not just a unidirectional flow of information and knowledge, so it's really a very fruitful thing, because there are so many similarities between the climate, what we are studying, and turbulence and combustion dynamics. There are some different scales, of course, different physical mechanisms behind, but the features that can be studied are very similar, and also the methods that can be applied are very similar. And because of these different fields, the different perspectives, we get new ideas. It was really very exciting to have this collaboration so far with Sujit. I'm really happy that we have this, and that I'm happy to continue this interesting endeavor here. Yeah. Thank you very much, Sujit.
Thank you, Norbert.
Any other questions or comments? If not, I would like to ask you to switch on your microphones, unmute your microphones, and join me in giving Sujit a big round of applause for this fascinating talk. Thank you very much, Sujit.
you very much. Thank you very much. Thanks everybody for coming.
Okay. Thank you. Bye-bye.
Bye-bye.
Bye.
Thank you. Bye-bye.
Thanks.
Thank you, Professor Sujit.
Bye,
Thank you, Professor
Sujit.
Maria,
We'll
for
talk to you
joining
later.
us.
Thank you, Ramesh, for coming. Thanks, Norm. Thanks all the audience. I think.
Have a nice evening.
Yeah, thank you.
Bye, Maria. Thank you so much. Sujit, I'd like to have a sort of a chat with you in the next few days. Are you very busy these days?
Well, busy, but I'll be most eager to.
Available, let me put it like this.
Yeah, I will be happy to talk to you. When do you want to speak? Till 20th is good. After
The
that,
20th. Let me just
20th. So tomorrow is okay. Also is 18, 19, 20. 21st, I'm going to Kerala for 2 weeks. So
okay. So 20 and tomorrow. Okay, tomorrow. When is a good time